Earthquakes have erased entire cities from the map of Peru, streets fractured, cathedrals collapsed inward. Towers that once reached toward the sky reduced to rubble in seconds. The ground here does not merely shake, it shifts, twists, and tears through anything rigid enough to resist it. And yet, in the midst of this destruction, something impossible remains. Walls. Not modern walls reinforced with steel, not structures designed with computer models and seismic simulations, but ancient walls, cut from stone, placed by hand, assembled without mortar, without binding, without anything that should logically hold them together. They stand in Cusco, where Spanish colonial buildings, once symbols of permanence, have fallen again and again over centuries of earthquakes, and beneath them, often quite literally, the older Inca stonework remains untouched. Foundations laid hundreds of years earlier continue to support structures that replaced them, as if the past is quietly holding up the present. They stand in Machu Picchu, high in the Andes, where the earth itself is unstable, where landslides and tremors are not rare events but recurring realities. The city has endured for nearly 6 centuries, its walls still aligned, still intact, still resisting forces that should have dismantled them long ago. And they stand at Sacsayhuaman, where colossal stones, some weighing over 100 tons, interlock with such precision that even now, after generations of seismic stress, their seams remain unbroken. There is a pattern here, not coincidence, not luck, a system. When there's an earthquake, only the restorations fall. The words of Richard Berger carry an unsettling weight, because they invert everything we assume about progress. The newer structures, the ones built with more advanced tools, better materials and formal engineering knowledge, fail first. The ancient ones endure. This is not just an archaeological curiosity, it is a contradiction. Modern construction relies on strength, reinforced concrete, steel frameworks, materials designed to resist force through rigidity, but rigidity has a weakness. When the earth moves, a rigid structure has only 2 choices: resist or break. These ancient walls seem to have chosen a third option. They do not resist in the conventional sense. They do not crack under pressure or collapse along predictable fault lines. Instead, they appear to absorb movement, to accommodate it, to exist in quiet negotiation with the shifting ground beneath them. And that raises a question that becomes more difficult to ignore the longer you look at them. How can structures built without mortar, without steel, without modern tools, outperform the very systems we consider the pinnacle of engineering? The Inca had no written language to record architectural theory, no formal equations describing stress distribution or wave dynamics, no instruments capable of measuring tolerance down to fractions of a millimeter. And yet, their walls demonstrate a level of performance that aligns uncannily with principles modern engineers would only formalize centuries later. This is not simply durability, it is behavior. A building that survives an earthquake is not necessarily unusual, but a structure that repeatedly endures across centuries in one of the most seismically active regions on Earth without significant degradation that demands a different kind of explanation. Because survival on that scale is rarely accidental. It suggests intention. But intention based on what? Observation? Trial and error across generations? Or an intuitive understanding of the Earth's movements, developed not through abstract theory, but through direct experience with a landscape that never stays still? There is another detail, often overlooked. Many of these Inca walls were not designed to stand alone. They became the foundations for later colonial structures. Spanish builders arriving in the 16th century recognized their stability and built directly on top of them cathedrals, homes, administrative buildings. And yet, when earthquakes struck, it was those additions that failed. Time and again the upper layers collapsed, the lower layers remained. It is as though 2 different philosophies of construction were placed in direct competition. One based on dominance, imposing structure onto the environment. The other based on adaptation, working with forces that cannot be controlled. And the outcome, repeated over centuries, is unambiguous. One breaks, the other endures. This is where the mystery deepens. Because if these walls were simply stronger, we could explain them. Strength is measurable. It can be quantified, tested, replicated. But what we are seeing is not just strength, it is resilience. A property that emerges not from resisting force, but from interacting with it in a more subtle way. And that is far more difficult to reverse engineer. There are no blueprints, no surviving manuals, no written explanations from the builders themselves. What remains are the stones, and the behavior they exhibit under conditions that destroy everything else. Which leaves us with a possibility that is both fascinating and unsettling, that these structures were not just built, they were understood in a way that may not fit neatly into the frameworks we use today. Because if modern engineering struggles to replicate what these walls achieve so effortlessly, then perhaps the limitation is not in the materials or the tools, but in the assumptions we bring to the problem. So what exactly are we looking at? Ancient architecture, refined through time and necessity, or evidence of a system, of knowledge, of observation, of design that we have not yet fully grasped? Subscribe to our channel if you love this content. That question draws the eye upward, away from the fractured streets of Cusco, into the mountains where the air thins and the terrain becomes less forgiving. There, balanced between two peaks, sits Machu Picchu, a city that appears less constructed than placed, as though it were always meant to exist exactly where it stands. At first glance, its walls seem simple, stone upon stone. No visible binding, no seams filled with mortar, no trace of adhesive holding the structure together. And yet, that absence is the defining feature. This is dry stone masonry in its purest form. No cement, no chemical bonds, no hidden reinforcements, only gravity and precision. Each stone is positioned with such care that its weight becomes part of a larger equilibrium, not a static balance but a distributed one, where every block contributes to the stability of those around it. Remove one and the system shifts. Place it correctly and the entire structure settles into coherence. What emerges is not a wall in the conventional sense, but a network of forces. The stability does not come from an external agent binding the stones together. It arises from the interaction between them, the friction of their surfaces, the angle of their placement, the pressure exerted downward and outward through the mass of the structure. It is, in effect, a self-balancing system. Modern construction often depends on introducing additional materials to compensate for imperfections. Mortar fills gaps, concrete unifies irregularities, steel reinforces weaknesses. These methods assume that materials alone cannot achieve sufficient precision or stability. Here, that assumption is absent. Instead, the solution is to eliminate the need for correction entirely. Each stone is shaped to meet its neighbors so precisely that there is no gap to fill. The contact surfaces are not merely flat, they are complementary. Slight curves, subtle angles, minute adjustments. Each one ensures that when two stones meet, they do so across a surface that maximizes friction and distributes load evenly. The result is a structure where force flows continuously through the material, rather than being interrupted or redirected by artificial bindings. Their intention was simply to build something efficient and functional. The result is impressive. The observation by Nicolas Estrada Mejia is almost understated, because what appears as simplicity is in reality a form of restraint, a decision to rely on fewer variables, fewer materials, fewer points of failure. This is not primitive construction, it is minimalist engineering at its highest level. To remove mortar is to remove certainty. Mortar guarantees cohesion, at least initially. It fixes stones in place, locks them into a rigid configuration. But that rigidity comes at a cost. Over time, mortar cracks. It weakens under stress, especially under the cyclical forces of earthquakes. When it fails, it does so abruptly, often taking the structure with it. By contrast, a dry stone system avoids that failure mode entirely. There is nothing to crack, nothing to degrade. Nothing to separate the stones from one another except the forces acting upon them, and those forces are precisely what the system is designed to accommodate. In Machu Picchu, this principle extends beyond individual walls. Entire terraces, stairways, and buildings participate in the same logic. The city is not a collection of isolated structures, but a continuous arrangement of interdependent elements, each one contributing to the overall stability. The mountain itself becomes part of the equation. Foundations are not carved to dominate the terrain, but to follow it. Stones are seated into the natural contours of the rock beneath, creating a direct interface between the constructed and the geological. Load is transferred not just through the walls, but into the mountain, dispersing stress across a much larger mass. It is a form of anchoring that does not rely on penetration or reinforcement, but on alignment. There is another consequence of this approach, one that becomes evident only under movement. Because the stones are not fixed by mortar, they retain a degree of independence. Not enough to shift freely under normal conditions, but enough to respond when the ground beneath them begins to move. In that moment, the entire structure transitions from static to dynamic. For a brief period, it is no longer a rigid assembly. It becomes responsive. Each stone can adjust slightly, redistributing stress, relieving pressure points, preventing the accumulation of forces that would otherwise lead to fracture. When the motion subsides, the stones settle back into place, guided by gravity and the geometry of their samperk surfaces. Nothing breaks. Nothing needs repair. The system resets itself. This behavior is difficult to achieve even with modern technology. Engineers design base isolators, dampers, and flexible joints to allow buildings to move safely during earthquakes. These solutions are complex, often expensive, and require precise calibration. At Machu Picchu, a similar outcome is achieved without any of those components. Not through added complexity, but through reduction. By relying on gravity, the builders eliminated the need for additional materials. By pursuing precision, they eliminated the need for correction. By allowing movement, they eliminated the risk of catastrophic failure. It is a chain of decisions that leads to an unexpected result, a structure that is both simple and sophisticated. And yet, there is an ambiguity that remains, because while the performance of these walls suggests an understanding of their advantages, the intentions of their builders are less certain. There is no surviving record that explicitly states a goal of earthquake resistance, no written doctrine explaining the choice to abandon mortar in favor of dry stone construction. It is possible that the method emerged from practicality. Mortar requires preparation, materials, and time. In a mountainous environment, where resources must be transported and conditions can change rapidly, simplicity may have been the most efficient solution. Stones are abundant, gravity is constant. Precision, though labor-intensive, offers permanence without dependency on additional substances. If the goal was efficiency and function, then the outcome, remarkable resilience, may have been an emergent property rather than a primary objective. But that possibility raises its own question. Because if such resilience can arise from a system designed for efficiency, then the line between intention and discovery becomes difficult to define. At what point does repeated success become understanding? And at what point does understanding become design? The walls of Machu Picchu do not answer these questions directly. They do not reveal the thought processes of their builders or the sequence of decisions that led to their final form. They simply exist, stable, balanced, enduring. A city held together not by what was added, but by what was deliberately left out. And in that absence, in the decision to rely on gravity and precision alone, there is a subtle implication. That strength, as we define it, may not have been the priority at all, which leaves a final consideration difficult to ignore. Why remove mortar, unless flexibility was more important than strength? Share your opinions and thoughts in the comments section. The absence of mortar leads to another, more unsettling observation, one that becomes clearer the longer you study the walls themselves. They are not built in straight lines, not in the way modern construction demands, not in the way bricks stack neatly, course upon course, forming predictable layers. Instead, the stones of Machu Picchu and Sacsayhuaman seem to resist uniformity altogether. Each block is shaped with multiple sides, 5, 6, sometimes 10 or 12, cut into irregular forms that defy repetition. This is polygonal masonry. At first glance, it appears almost chaotic. No consistent height, no repeating pattern, no obvious symmetry. And yet, when viewed as a whole, the structure feels coherent, deliberate, as though governed by a set of rules that are not immediately visible. Each stone is unique. Each edge is angled to meet another at a specific point. Joints curve and bend rather than running straight. Contact surfaces shift direction, sometimes multiple times within a single block. It is not a pattern you can predict by looking at one section and extending it outward. Every segment is an adaptation to its immediate surroundings. What emerges is not a wall assembled from identical units, but a continuous field of interlocking shapes, and it is precisely this irregularity that begins to explain its behavior. In modern construction, regularity is efficiency. Bricks are standardized because they are easy to produce, easy to transport, and easy to assemble. But that regularity introduces a structural weakness. Straight horizontal joints create continuous lines across the wall, lines along which stress can travel without interruption. When an external force is applied, especially during an earthquake, those lines become fault paths. Energy moves through the structure along the path of least resistance. In a brick wall, that path is often a straight seam. Once a crack forms, it propagates quickly, following the joint, splitting the structure along predictable lines. The failure is not random. It is guided by the geometry itself. Polygonal masonry disrupts this process entirely. There are no long, continuous seams, no straight horizontal layers extending across the structure. Instead, every joint changes direction. Every contact surface introduces a new angle, a new orientation, a new resistance to the movement of stress. When force enters such a system, it cannot travel in a straight line. It is deflected, divided, redistributed. Energy that would normally concentrate along a single plane is instead dispersed across multiple pathways. Each stone shares the load with several neighbors, transferring force in different directions simultaneously. The result is a form of structural redundancy, not through repetition, but through complexity. In practical terms, this means that there is no single point of failure, no predictable crack line, no easy way for the structure to come apart. This behavior aligns closely with principles that only much later would be formalized in the study of fracture mechanics. In modern materials science, engineers design composites with irregular internal structures precisely to prevent crack propagation. By interrupting linear pathways, they increase toughness, the ability of a material to absorb energy without failing. In this sense, the walls of the Inca are not just resisting force, they are managing it. The comparison becomes even more striking when considering how advanced materials are engineered today. Certain ceramics, for example, are embedded with microscopic structures that force cracks to twist and turn as they propagate. Each deviation consumes energy, slowing the fracture, sometimes stopping it entirely. At a vastly larger scale, polygonal masonry achieves something similar. The stones act as macroscopic units in a system that behaves like a composite material. Their irregular shapes function as barriers to crack growth. Their interlocking edges ensure that even if movement occurs, it does not translate into separation. It is a form of design that prioritizes resilience over simplicity. And yet, it was achieved without the theoretical framework that modern engineers rely on. There were no equations describing stress intensity factors, no computational models predicting fracture behavior, no laboratory experiments measuring material toughness. Only stone, only observation, only the accumulated experience of working within a landscape where failure would have been immediately visible and often catastrophic. This raises an important distinction. Understanding does not always begin with theory. It can emerge from repetition, from building, observing, adjusting, and building again. If early structures failed along straight seams, that failure would have been evident. Cracks would form, walls would collapse. Over time, builders may have noticed patterns, subtle at first, then increasingly clear. Certain arrangements held, others did not. Gradually, a preference for irregularity could have developed, not as an abstract principle but as a practical response, each generation refining what the previous one had learned, each structure becoming a record of what worked. In such a process, complexity is not introduced for its own sake. It is the result of eliminating weaknesses. Straight lines become less common because they fail. Irregular joints become more common because they endure. What remains, after many iterations, is a system that appears sophisticated, not because it was conceived as such, but because it has been shaped by constraint. And yet, there is another possibility, that the builders were not merely reacting to failure, but anticipating it. That they recognized, perhaps intuitively, that the earth beneath them was unstable, and that any structure designed to survive would need to avoid the very patterns that made other walls vulnerable. If that is the case, then polygonal masonry is not just an evolved technique, it is a deliberate strategy, a way of constructing order out of irregularity, a way of embedding resilience directly into the geometry of the structure. There is a subtle elegance in that idea because it suggests that strength does not always come from uniformity. Sometimes it emerges from variation, from the refusal to repeat a single form, from the willingness to adapt each element to its specific context. Standing before these walls, the eye struggles to follow the lines. There is no easy rhythm, no simple pattern to trace, and yet the mind recognizes that this apparent disorder is not random, it is controlled. Each stone belongs exactly where it is. Each angle serves a purpose, even if that purpose is not immediately visible. The longer one looks, the clearer it becomes that this is not an absence of design. It is a different kind of design, one that does not reveal itself through symmetry or repetition, but through performance, through the quiet fact that these walls remain intact where others have failed. And that brings the question into sharper focus. Because if this geometry achieves what modern fracture-resistant materials are designed to do, if it interrupts stress, disperses energy, and prevents catastrophic failure, then the gap between ancient practice and modern theory begins to narrow, not in tools, not in materials, but in outcome, which leads to a possibility that is difficult to dismiss. Did the builders of these walls intuitively understand principles of structural physics that would only later be formalized, or did they arrive at the same solutions? Through generations of experimentation, guided not by theory, but by the persistent, unforgiving feedback of the earth itself. If the geometry disrupts force, then the precision holds it together. Because irregular shapes alone are not enough. Without exact contact, without surfaces that meet cleanly and completely, even the most complex arrangement would fail. Gaps would introduce instability. Edges would grind, shift, and eventually separate under stress. The entire system depends on something far less visible, but far more demanding. Accuracy, not approximate, not functional in a loose sense, but exact, down to a level that challenges even modern expectations. At sites like Sacsayhuaman and Machu Picchu, the seams between stones are often so tight that a blade cannot pass between them. In many cases, even a thin sheet of paper meets resistance. Measurements taken in detailed studies suggest tolerances frequently below 1 millimeter. In certain contact surfaces, flatness approaches 1/10 of a millimeter, levels that, in modern engineering, require controlled tools, calibrated instruments, and stable working environments. Here, those conditions did not exist. And yet the result is undeniable. Each stone is shaped not just to fit, but to fit only once. Remove a block from its position, and it cannot simply be replaced with another. Its surfaces are not standardized, they are not interchangeable. Every face is tailored to the exact contours of the stones around it. This is not modular construction, it is relational construction, a process in which each element derives its form from its neighbors rather than from a predefined template, which leads to a paradox that becomes increasingly difficult to resolve. There are no surviving blueprints, no written plans outlining dimensions, angles, or sequences of placement. The Inca did not leave behind architectural drawings or mathematical descriptions of their methods. There is no evidence of standardized measurement systems comparable to those used in other ancient civilizations. No units carved into tools, no reference scales etched into stone. Even more striking is the absence of tools capable of producing such precision. The Inca did not possess iron or steel. Their implements were primarily made of stone, bronze, and other relatively soft materials. Hammerstones could shape rock through repeated impact. Sand and water could be used as abrasives to smooth surfaces, but neither method lends itself easily to the kind of fine control required to achieve sub-millimeter tolerances across irregular, multi-angled faces. And yet, the stones meet as though they were machined. I've never seen such precision with primitive tools. The statement, echoed by engineers and observers encountering these walls for the first time, reflects not disbelief, but a kind of recalibration. Because what is being observed does not align with the expected capabilities of the available technology. The question is not whether it was done. It was. The question is how. One explanation lies in process rather than tools. Instead of cutting stones to predetermined shapes, builders may have worked iteratively. A stone would be roughly shaped, then placed against its intended neighbors. Points of contact would be identified, perhaps marked with pigments, perhaps revealed through subtle friction. The stone would then be removed, adjusted, and placed again. This cycle would repeat, again and again, each iteration refining the fit, each adjustment bringing the surfaces closer into alignment. It is a method that does not rely on measurement in the abstract, but on direct comparison. The stone becomes its own reference. The surrounding structure defines the necessary corrections. Precision emerges not from external standards, but from repeated interaction between physical forms. Such a process would be slow, labor-intensive, demanding a level of patience and attention that modern construction rarely accommodates. But it would also be adaptive, capable of producing exact fits without requiring precise instruments. There is evidence to support this approach. Some stones show subtle markings, shallow depressions, or traces of abrasion consistent with repeated handling and adjustment. In certain cases, small protrusions, sometimes referred to as nubs, remain on the surfaces of blocks, possibly used for lifting or positioning during this iterative process. Still, even with such methods, the scale of the achievement remains difficult to reconcile. These are not small stones shaped on a workbench. Some weigh tens of tons. Others, particularly at Sacsayhuaman, exceed 100. Manipulating such masses with enough control to allow repeated fitting requires coordination, planning, and an understanding of leverage, and balance that goes far beyond simple trial and error. And yet, attempts to replicate this precision have struggled. In the 20th century, engineers and masons attempted to reproduce polygonal masonry using both traditional and modern tools. In the 1930s, experimental efforts sought to apply known Inca techniques to create similar joints. The results fell short. Even with the benefit of hindsight, even with access to metal tools and controlled conditions, achieving the same level of seamless integration proved elusive. Later experiments, incorporating modern cutting equipment and lifting machinery, improved the outcome but still failed to capture the organic complexity of the original work. The stones could be cut flat, they could be aligned, But the subtle curvature, the shifting angles, the way each face adapts to multiple neighbors simultaneously, these qualities remained difficult to reproduce. This suggests that the challenge is not purely technical, it is conceptual. Modern construction tends to separate design from execution. Plans are drawn, measurements defined, and materials are shaped to fit those specifications. Precision is imposed from the outside, guided by abstract representations. In the Inca approach, design and execution appear to merge. There is no clear boundary between planning and building. The form evolves as the structure takes shape. Decisions are made in response to immediate conditions rather than predetermined diagrams. Precision in this context is not the result of measurement, it is the result of attention, of continuous feedback between the builder and the material, of an intimate familiarity with stone, how it fractures, how it responds to impact, how its surface changes under abrasion. It is a different kind of knowledge, not easily documented, not easily transferred outside the context in which it was developed, and perhaps not easily recovered once lost. Because if the process depends on a chain of experience, skills passed from one generation to the next, refined through practice rather than recorded in writing, then its disappearance becomes understandable. When that chain is broken, the method vanishes with it. What remains are the results: silent, precise, unyielding, stones that fit so perfectly they seem almost fused, yet remain entirely separate. A level of craftsmanship that challenges not only our assumptions about ancient capabilities, but our understanding of what precision itself requires. And so the paradox persists: no standardized units, no advanced tools, no written plans, only stone, shaped and reshaped until it meets its neighbors without flaw. Which leads to a final question, as unavoidable as it is difficult to answer. How do you achieve near-perfect precision without measurement systems? Subscribe to our channel if you love this journey. Precision alone does not explain survival. A perfectly fitted wall, if rigid, should still fail when the ground beneath it begins to move. Because earthquakes do not test strength in the way most forces do. They do not push in a single direction or apply a steady load. They arrive as waves, vibrations that pass through the earth, shifting everything they touch in rapid, unpredictable motion. And it is here that the behavior of these walls becomes even more unusual. The stones are not fixed. They are not locked in place by mortar or fused into a single, immovable mass. Instead, they retain a subtle independence. Each block, though precisely shaped, can move, very slightly, relative to its neighbors. Not enough to be visible under normal conditions, but enough to matter when the ground begins to tremble. At sites like Machu Picchu and Sacsayhuaman, this characteristic transforms the walls from static structures into kinetic systems. They do not resist motion in the conventional sense, they participate in it. To understand why this matters, it is necessary to consider what an earthquake actually is. Beneath the surface, tectonic plates shift, releasing energy that travels outward as seismic waves. These waves move through the ground in multiple forms, some compressing and expanding the material, others shearing it side to side. When they reach a structure, that structure becomes part of the medium through which the waves propagate. A rigid building attempts to oppose this motion. Its components are fixed together, designed to maintain their relative positions. When the ground moves, the structure lags behind, then catches up, then lags again. This mismatch creates internal stresses. Energy accumulates at joints, corners, and weak points. If the stress exceeds the strength of the materials, something gives. Cracks form, sections separate, collapse follows. In such systems, rigidity is not an advantage. It is a liability, a more. Flexible structure behaves differently. Instead of resisting the motion, it allows it. Components shift, bend, or slide in response to the incoming waves. Energy is not concentrated in one place but spread across the structure. Each movement absorbs a portion of the force, reducing the load on any single point. The difference can be understood through a simple analogy. A sheet of glass, held rigid, will shatter under sudden stress. Its structure allows no internal movement. The force has nowhere to go except through fracture. A woven fabric, by contrast, can be pulled, twisted, and compressed. Its fibers move relative to one another, redistributing the force. It may deform, but it does not break in the same way. The walls of the Inca behave more like the fabric. Their stones, though heavy and tightly fitted, are not bonded. They rely on gravity and friction, which means that under sufficient force, they can shift microscopically. Edges press, release, and settle again. Contact surfaces slide just enough to prevent the buildup of destructive stress. And when the shaking stops, the system returns to equilibrium. The stones settle back into their original positions, guided by their geometry and the constant pull of gravity. There is no need for repair, no cracks to seal, no weakened joints to reinforce. The structure resets itself. This behavior resembles, in a fundamental way, what modern engineers attempt to achieve with seismic isolation systems. In contemporary buildings, especially in earthquake-prone regions, designers incorporate devices that allow the structure to move independently of the ground. Base isolators, for example, are placed between a building and its foundation. They absorb and deflect seismic energy, reducing the forces transmitted upward. Dampers dissipate energy through controlled movement, converting kinetic energy into heat. Flexible joints allow different parts of a structure to move without tearing themselves apart. These systems are complex. They require precise calculation, specialized materials, and ongoing maintenance. Yet the underlying principle is simple: allow movement to prevent destruction. In the walls of Sacsayhuaman, a similar principle appears to be at work, without any of the modern components. The stones themselves act as isolators. Their interfaces become the points where energy is absorbed and redirected. The entire wall functions as a distributed network of micro-adjustments. No single element carries the full burden. No single joint becomes the point of failure. It is a system that does not eliminate motion, but manages it. There is a subtlety here that is easy to overlook. The effectiveness of this system depends not only on the ability of the stones to move, but on the precision with which they are shaped. Too loose, and the structure would lack stability. Stones would shift excessively, leading to gradual deformation or collapse even without seismic activity. Too tight, and the system would behave more like a rigid block, losing its ability to absorb energy. The balance is exact. Each stone must fit closely enough to maintain alignment under normal conditions, yet loosely enough to permit micro-movements under stress. This is not an accidental property. It emerges from the interaction between geometry, mass, and friction. And it suggests a level of control that goes beyond simple construction, because achieving such a balance requires not only shaping stones to fit, but understanding how they will behave over time, under varying conditions, under forces that may not occur for years or even decades after the structure is completed, which brings the question back to intention. Did the builders of these walls anticipate earthquakes? They lived in a region where seismic activity is frequent. The Andes are part of the Pacific Ring of Fire, a zone defined by tectonic instability. Over generations, the effects of earthquakes would have been observed, remembered, and integrated into cultural knowledge. It is reasonable to assume that builders understood, at least in practical terms, that the ground was not stable. But understanding that earthquakes occur is not the same as designing structures to withstand them. There is no surviving record that explicitly describes seismic strategy. No text that outlines a theory of wave propagation or energy dissipation. No direct evidence that the builders conceptualized their work in terms of kinetic systems. And yet, the outcome aligns with those principles. Either through deliberate design or through iterative refinement, the walls exhibit a behavior that modern engineering recognizes as effective. They move, they absorb, they endure. And in doing so, they challenge a fundamental assumption that stability requires rigidity. Instead, they suggest that resilience may depend on the ability to adapt, even at the level of stone. Which leaves an open question, one that cannot be resolved by observation alone. Were these walls conceived with an understanding of the forces they would face, or did their resilience emerge gradually, discovered through generations of building, failure, and quiet correction, until the final form no longer broke under the shifting of the earth? The movement of the stones explains how the walls survive. But the walls are only one part of a larger system, one that extends beyond individual blocks into the very shape of the architecture itself. Because when you step back from the stone surfaces and look at the structures as a whole, another pattern begins to emerge. Nothing is quite straight. At Machu Picchu, doorways narrow slightly toward the top. Windows follow the same form. Openings that might appear rectangular at first glance reveal themselves, on closer inspection, to be subtly trapezoidal. The base is wider, the top is narrower, the sides are not vertical but incline inward, meeting the lintel at an angle that feels almost imperceptible. The walls themselves follow a similar logic. They do not rise perfectly upright. Instead, they lean inward, typically by 3 to 5 degrees. Over the height of a wall, this creates a quiet convergence, an inclination toward the center of mass. Corners too resist the expected geometry. Rather than sharp 90-degree intersections, many are slightly rounded or beveled. Edges soften, angles blur just enough to disrupt the rigid continuity that defines most built environments. Individually, these choices might seem aesthetic. Collectively, they form a coherent structural language. And when viewed through the lens of physics, that language begins to reveal its function. A vertical wall, perfectly straight, places its center of gravity directly above its base. Under static conditions, this is stable. But introduce lateral motion, such as the horizontal acceleration of an earthquake, and the situation changes. The higher the center of mass, the greater the leverage exerted by that motion. The structure becomes more susceptible to tipping or to the amplification of oscillations. By inclining the walls inward, the center of gravity shifts, not dramatically, but enough to matter. The mass of the wall is directed toward its own foundation, creating a self-stabilizing tendency. When lateral forces act upon it, the geometry encourages a return to equilibrium rather than a departure from it. It is a subtle correction, embedded not in material, but in form. The trapezoidal openings operate on a related principle. A rectangular doorway introduces points of weakness at its upper corners. Stress concentrates at these junctions, particularly under dynamic loading. Cracks, when they form, often originate here, propagating outward along predictable lines. A trapezoidal shape alters this behavior. The inward-sloping sides distribute stress more evenly. Forces are redirected along the angled edges, reducing the likelihood of concentration at a single point. The narrower top also means less mass is suspended above the opening, decreasing the load that must be supported. In effect, the shape guides the forces. It does not eliminate them, but it changes how they move through the structure. Rounded corners contribute in a similar way. Sharp angles are natural sites for stress accumulation. They interrupt the flow of force, creating discontinuities where energy can build. In materials science, this is a well-understood phenomenon. Stress concentration factors increase dramatically at abrupt changes in geometry. By softening these transitions, the Inca builders reduced those concentrations. Forces move more smoothly around curves than they do across corners. The structure behaves as a continuous system rather than a collection of discrete elements joined at vulnerable points. These are not isolated techniques. They interact. The inward lean of the walls complements the flexibility of the stone joints. The trapezoidal openings work in concert with the irregular masonry to prevent the formation of linear fracture paths. The rounded corners ensure that even under stress, There are no obvious points at which failure can begin. What emerges is not a set of features, but a strategy. A way of building that considers not only how a structure stands, but how it responds when standing is no longer enough. They made architecture that was in dialogue with the landscape. The observation, offered by architectural historian Stella Nair, captures something that extends beyond engineering. Because the landscape in question is not static. It is a region defined by movement, tectonic, climatic, geological. To build here is to engage with those forces, whether consciously or not. And the Inca appear to have done so with remarkable consistency. Across different sites, from the high terraces of Machu Picchu to the massive fortifications of Sacsayhuaman, the same architectural principles recur, the same inclinations, the same trapezoids, the same refusal to rely on perfect symmetry or rigid alignment. This suggests that the approach was not experimental in the narrow sense. It was systemic, a set of design rules applied across contexts, adapted to local conditions, but rooted in a shared understanding of how structures behave. Whether that understanding was formalized, taught explicitly, codified in some now lost form, or transmitted through practice remains uncertain. The Inca left no written treatises on architecture. Their knowledge systems were largely oral, embodied in the work of builders and passed through apprenticeship rather than documentation. But the consistency of the results implies a degree of intentionality that is difficult to dismiss. These are not random variations, they are controlled deviations from what might otherwise be expected. And they work. Modern seismic engineering often employs similar concepts. Buildings are designed with tapered profiles to lower their centers of gravity. Openings are reinforced or shaped to reduce stress concentrations. Corners are treated carefully to avoid creating knockout of weakness. Entire structures are analyzed not just for their ability to stand, but for their behavior under dynamic loading. In the Inca context, these considerations appear without the accompanying calculations. No equations are inscribed on the stones. No models survive to illustrate the reasoning. And yet, the principles are there, embedded in the geometry itself. It raises an uncomfortable possibility. That effective engineering does not always require formal theory. That repeated observation, combined with careful adjustment, can produce solutions that align with physical laws without ever being expressed in those terms. Over generations, builders would have seen what failed: walls that cracked, openings that collapsed, corners that gave way under stress. Each failure would offer information, each reconstruction an opportunity to refine the approach. Gradually, patterns would emerge. Certain shapes would prove more resilient, certain angles more stable, certain configurations more forgiving under movement. What begins as adaptation becomes tradition. What begins as correction becomes design. And eventually the distinction between aesthetic choice and structural necessity begins to blur. Because when a form consistently performs better, it is no longer just a preference, it is a principle, which leads to a final ambiguity that lingers in every inclined wall and narrowing doorway. Were these shapes chosen because they were beautiful, or because, over time, they revealed themselves to be the only forms that would endure? What we see in these walls is only half the structure. The outer faces, those tightly fitted polygonal blocks, draw the eye. Their precision is undeniable. Their seams are almost seamless. But behind that exterior lies something less obvious and arguably more important. The interior is not solid stone in the modern sense. It is often composed of smaller stones, rubble, clay, compacted earth, materials packed together to form a dense core. In many Inca walls, especially at monumental sites such as Sacsayhuaman and within the broader complex of Machu Picchu, this layered construction becomes clear through archaeological study and partial exposure. The result is not a monolithic block, it is a composite system. This distinction is critical. A monolithic structure behaves uniformly. Force travels through it in predictable ways. When stressed beyond its capacity, failure can propagate through the entire mass. A composite structure behaves differently. It combines materials with distinct mechanical properties to achieve performance that no single material could provide alone. Modern engineering relies heavily on this principle. Reinforced concrete, for example, pairs the compressive strength of concrete with the tensile strength of steel. Each component compensates for the weaknesses of the other. In the Inca walls, the outer stones provide rigidity, alignment, and surface integrity. The inner fill provides mass, energy absorption, and internal damping. Together, they form a layered system. When seismic waves enter the structure, the dense exterior blocks distribute the initial force across their interlocking surfaces. But not all energy is transmitted directly through solid stone. Some of it encounters the internal core, where smaller elements can shift microscopically, compress, and settle. This internal flexibility functions as a form of shock absorption. Instead of allowing vibrations to concentrate, the layered composition disperses them. Energy moves through multiple pathways, across outer joints into the core and back again, losing intensity with each transition. The structure does not behave as a rigid object. It behaves as a system with internal degrees of freedom. Modern earthquake engineering uses similar concepts. Base isolation systems allow buildings to move independently from their foundations. Dampers are installed within structures to absorb and dissipate kinetic energy. Layered materials are designed to interrupt vibration transmission. Even in high-performance architecture, engineers intentionally combine stiff and flexible components to control how force flows. The principle is consistent: rigidity alone is not enough. Energy must be managed. What makes the Inca approach remarkable is that this composite logic appears without visible technology in the modern sense. There are no metal reinforcements embedded in the walls, no synthetic materials, no engineered shock absorbers. The damping mechanism is achieved through geometry, mass distribution, and material layering. The outer shell provides precision and structural continuity. The interior provides controlled variability. This combination creates a system that is both stable and adaptable. It also raises a subtle question. If the interior is largely hidden, why invest so much effort in the exterior? The outer stones required extraordinary labor, each block shaped with care, each joint refined to achieve near-perfect contact. This level of craftsmanship would not have been necessary if the wall's primary function was simply to hold rubble in place. From a purely utilitarian perspective, a simpler facade could have sufficed. Yet the exterior is meticulously constructed. The visible surfaces are the most precise. This suggests that the outer layer served multiple purposes. Structurally, it forms the load-bearing envelope of the wall. It stabilizes the core, constraining it within a defined geometry. By tightly interlocking the exterior, builders effectively created a rigid frame around a more flexible interior. This containment allows the core to absorb energy without dispersing material outward. In mechanical terms, the system resembles a constrained composite, where an outer shell governs deformation while the inner material dissipates stress. But there may be more to the precision than mechanics alone. In many Inca sites, architectural expression carried social and cosmological significance. The appearance of order, permanence, and control over stone may have conveyed authority and alignment with natural forces. A precisely fitted exterior would have demonstrated mastery, not just of materials, but of the environment itself. Stone becomes both structure and statement. The outer perfection could therefore be simultaneously structural and symbolic. Structurally, it ensures stability. Symbolically, it communicates competence, coherence, and harmony with the landscape. These interpretations are not mutually exclusive. In complex systems, function and meaning often overlap. The interior fill, though hidden, is not careless construction. It is compacted deliberately. The layering of materials increases friction within the core, further enhancing energy dissipation. Smaller stones wedge between larger ones, reducing voids and improving density. Clay and fine materials bind the mass, limiting excessive movement while still permitting micro-adjustments under stress. The result is a wall that behaves dynamically, externally rigid, internally adaptable. Such a configuration aligns closely with modern understanding of seismic resilience. Engineers now recognize that distributing stiffness across a structure rather than concentrating it in one element improves performance under dynamic loads. Systems that combine mass, damping, and controlled flexibility tend to outperform purely rigid designs. The Inca achieved this without computational modeling, without finite element analysis, without formalized structural theory, which does not necessarily imply that the principles were unknown. It may indicate that they were understood through empirical practice, through repeated observation of how different construction methods performed in a seismic environment. Over generations, builders would have noticed that walls constructed with a tightly fitted exterior and a compacted core endured better than those built differently. Such insights, once validated by experience, become tradition. And tradition, in engineering cultures, can function as a powerful repository of knowledge. Still, the contrast remains striking. The outer layer is almost obsessive in its precision. The inner core is functional, dense, and responsive. Together, they form a dual system, one part visible, one concealed, one refined, one absorptive, and that duality returns us to a deeper ambiguity. Was the outer perfection necessary purely for structural reasons, providing containment, alignment, and resistance to lateral forces? Or did it also serve a broader purpose, projecting stability and intentionality in a world shaped by environmental unpredictability? At sites like Machu Picchu, where terraces descend into steep valleys and seismic activity is a constant presence, architecture becomes more than shelter. It becomes a dialogue between human design and geological motion. Perhaps the outer precision represents the visible commitment to order, while the interior flexibility reflects an understanding of reality's instability. One asserts control, the other acknowledges movement. Together they create balance. And yet, even now, as we examine cross-sections and analyze material composition, the full reasoning behind this layered system remains partially obscured, just as the interior of the walls themselves is hidden behind their immaculate faces. Was the perfection we see simply the necessary envelope for a resilient core, or was it also an intentional expression of harmony, where engineering and symbolism converged in stone? What are your thoughts about this? Share with us in the comments section. If the walls themselves seem improbable, the question of how the stones arrived is even more demanding, because precision is only half the story. Before a single block could be shaped, it had to be extracted, transported, and positioned. And in many cases, these stones were not modest pieces of manageable size. At monumental sites such as Sacsayhuaman, some blocks weigh well over 100 tons. Certain estimates place the largest stones at more than 200 tons. These are not decorative elements, they are structural foundations, and they were moved across distances that could reach 20 miles or more from their original quarries, often through steep Andean terrain, valleys, ridges, unstable slopes, and narrow passes. There were no metal wheels in use, no draft animals capable of hauling such loads, no iron tools to fabricate heavy mechanical lifting systems. The mainstream explanation relies on human labor combined with simple machines, ramps, levers, ropes, wooden rollers. These methods are historically plausible and consistent with technologies known in the region. Teams of workers could, in theory, drag stones across prepared pathways, using coordinated effort and mechanical advantage to incrementally shift massive loads. In flatter terrain, such systems can function effectively, but the Andes are not flat. The landscape surrounding sites like Machu Picchu is defined by steep gradients, unstable soil, and dramatic elevation changes. Constructing continuous ramps over such distances would require enormous quantities of material. The ramps themselves would need to be engineered, stabilized, and maintained, only to be dismantled afterward. And even then, the physics becomes unforgiving. A 200-ton stone does not respond gently to uneven ground. Friction increases dramatically on inclines. The force required to move such a mass uphill grows with both weight and slope angle. On steep terrain, the required pulling force quickly exceeds what even large coordinated teams can generate without advanced mechanical systems. The logistical challenge is not just about moving weight, it is about controlling it. Transporting a massive block across uneven ground introduces risks, tipping, cracking, sliding uncontrollably. Without wheels or standardized heavy lifting equipment, maintaining stability during movement would demand continuous adjustment and precise coordination. This is where the chronicler's accounts become particularly striking. The Spanish observer Pedro Chiesa de Leon wrote of stones so large that no man could imagine how they were moved. His words reflect not just admiration, but genuine uncertainty. To European eyes of the 16th century, the scale of these constructions defied familiar categories of engineering. It is important to approach such statements carefully. Chroniclers were not engineers. Their descriptions often mix observation with interpretation, yet even allowing for exaggeration, the physical evidence remains. Extremely large stones were transported and placed with remarkable accuracy. The real difficulty lies not only in the size of the blocks, but in the terrain itself. Ramps require stable foundations. In mountainous environments prone to erosion and seismic activity, constructing long, durable inclines presents its own engineering demands. Each ramp would need to support not just static weight, but dynamic forces during movement. The steeper the incline, the greater the effort required. The longer the ramp, the greater the volume of material needed to build it. Some scholars propose that ramps were used in shorter segments, combined with incremental positioning. Stones may have been moved gradually, shifted across prepared surfaces, and raised step by step, using lever systems and coordinated labor. This approach aligns with known capabilities of large-scale human organization. The Inca state was highly structured, with labor systems that mobilized communities for public works. Roads connected regions across vast distances. Agricultural terraces reshaped entire mountainsides. The administrative capacity required to coordinate such efforts was substantial. Large teams, operating in disciplined units, could apply sustained force over time. With enough people, even extremely heavy stones can be moved incrementally using simple mechanical advantage. But the challenge extends beyond force alone. It is also about sequencing. Moving a stone 20 miles is not a single event. It is a chain of controlled actions: extraction from the quarry, initial shaping, loading, transport across terrain, temporary staging, final shaping, and precise placement. Each stage must align with the next. Any miscalculation could damage the stone or delay the project. Quarries located far from construction sites add complexity. Transport routes must be identified and maintained. Elevation changes must be managed. River crossings, if present, require bridges or coordinated transport strategies. In mountainous environments, these logistical demands multiply. The engineering challenge, therefore, is twofold. First, the stone must survive extraction and transport without fracture. Second, it must arrive at the site in a condition suitable for final precision fitting. This suggests that some shaping occurred near the quarry, reducing weight before transport. It also implies that rough dimensions were established early in the process, with final adjustments made on site. Such staged refinement would minimize the risk of damage during movement. Even so, the scale remains extraordinary. The coordination required to move multi-ton stones through steep terrain without modern machinery represents a remarkable organizational achievement. It implies not only physical capability but communication, planning, and sustained communal effort. And yet, when examining the completed structures, the focus often shifts to the walls themselves, their geometry, their precision, their seismic resilience. But without transport, none of that would exist, which raises a deeper perspective. Perhaps the most impressive aspect of these monuments is not how the stones fit together, but how they were brought together at all. Because the walls represent the final stage of a much larger system: extraction, logistics, workforce coordination, engineering knowledge applied across multiple domains. The true complexity may lie in that process, in the ability to integrate geography, labor, material science, and structural design into a single coherent operation. And if so, then the mystery extends beyond stonework. It touches the organization that made it possible. The question becomes not merely how the walls stand, but how a civilization without wheels, without draft animals, and without modern machinery managed to relocate stones of immense weight across some of the most challenging terrain on Earth. Is the real enigma carved not into the walls, but into the path that led the stones to their place? Among the many stones that define the architecture of Cusco, one has become almost emblematic of the Inca approach to structural precision. It is commonly referred to as the 12-angled stone, located within a wall that once formed part of a significant Inca palace complex in the historic center of Cusco. Unlike the larger polygonal blocks at Sacsayhuaman, this stone is not monumental in scale. It weighs approximately 6 to 7 tons, still immense by modern standards, but modest compared to the largest transported blocks. What makes it extraordinary is not its mass, but its geometry. The stone is cut with 12 distinct sides, each carefully shaped to interlock with the surrounding masonry. It does not sit within a simple rectangular frame. Instead, its edges are angled, stepped, and fitted so precisely that the seams are remarkably tight. The block appears almost organic in how it integrates with the wall, as though it were grown into position rather than placed. The material itself is significant. It is carved from diorite, an igneous rock known for its hardness and durability. Diorite is significantly more resistant to abrasion than many sedimentary stones. Working such material requires persistence and effective use of abrasives. The Inca did not rely on iron tools. Instead, they likely employed stone tools, hammerstones, and sand-based grinding techniques to gradually shape the surface. The precision of the fit is striking. Each of the 12 sides meets its neighbors without visible gaps. The surrounding stones conform to its irregular edges, forming a continuous surface. There are no straight seams running across the wall. The geometry ensures that no single joint aligns in a way that could propagate a crack. From a structural perspective, this multi-angled configuration distributes force across multiple planes. When lateral stress is applied, such as during seismic activity, each angled surface redirects a portion of the energy into adjacent stones. Because the edges vary in orientation, the stress cannot travel in a single uninterrupted line. Instead, it is broken up and dispersed throughout the surrounding structure. This is not accidental behavior, it is the direct consequence of geometry. In structural mechanics, the more complex the interlocking pattern, the more pathways exist for force redistribution. The 12-angled stone functions as a central node in a network. Each of its 12 contacts contributes to load sharing. Rather than concentrating stress at one or two points, the design spreads it broadly. This reduces the likelihood of fracture along predictable seams. It also enhances stability under uneven loading conditions. If the surrounding wall shifts slightly, the multiple contact angles allow for minute adjustments without loss of integrity. The stone becomes both anchor and integrator, binding different directions of force into a unified system. Its location within a prominent wall adds another layer of significance. In many architectural traditions, exceptional stones serve both structural and symbolic purposes. The 12-angled stone stands out visually within its context. Visitors often notice it immediately, not because it is larger than its neighbors, but because its complexity contrasts with the surrounding geometry. Such prominence suggests intentional placement. Within the broader architectural environment of Inca urban design, precision often carried meaning. Stone was not merely a building material, it was a medium of cultural expression. The careful shaping of a block could signify status, authority, or connection to cosmological principles. The number 12 itself invites reflection. Across many cultures, 12 carries calendrical associations, 12 months, 12 divisions of time. While there is no definitive evidence linking this stone directly to a calendar system, the symbolic resonance of the number cannot be ignored. The Inca maintained sophisticated calendrical knowledge, tracking solar cycles for agricultural and ceremonial purposes. Whether the 12 sides were intended to reference temporal divisions, or whether the number emerged purely from structural necessity, remains uncertain. What is clear is that the geometry works. Each angle is not merely decorative, it contributes to stability. By increasing the number of interlocking surfaces, the stone enhances resistance to movement in multiple directions. It exemplifies the principle that complexity, when controlled, can strengthen a system. This is particularly relevant in a seismic environment. Cusco lies in a region shaped by tectonic activity. Earthquakes generate multi-directional forces. A structure that can respond effectively to such forces must accommodate stress from varying angles. The 12-angled stone, with its 12 distinct faces, provides multiple planes for force distribution. It behaves as a structural hub, not isolated, but integrated. Its presence within the wall demonstrates that precision was not limited to large polygonal blocks. Even mid-sized stones received meticulous attention. The same principles observed in massive fortifications appear here at a finer scale. This consistency suggests a unified architectural philosophy. Whether in monumental terraces or urban walls, the approach remains the same: interlocking geometry, tight tolerances, and stress-dispersing design. Yet despite its technical sophistication, the stone also holds cultural identity. Over centuries, it has become a symbol of Cusco itself. It is frequently cited in discussions of Inca craftsmanship, representing the ingenuity attributed to the civilization. Its survival through earthquakes and colonial transformations reinforces its status as a testament to durability. The stone's endurance adds to its significance. It has remained in place through seismic events that damaged surrounding structures. Its survival is not merely aesthetic, it is empirical evidence of the effectiveness of the design principles it embodies. And still, questions persist. Was this level of angular complexity developed purely through iterative experimentation? Did builders observe that increasing interlocking surfaces improved resilience, or did they possess a conceptual understanding of force distribution that guided such designs intentionally? There is no written explanation from the Inca describing their reasoning. Only the stone remains. Its 12 sides speak through geometry rather than text. Each edge contributes to a system that resists linear fracture. Each angle ensures that stress must change direction, preventing the formation of a single failure plane. The result is a block that does not simply sit within a wall, but actively participates in the structural integrity of the entire assembly. It stands as a microcosm of the broader masonry system. In one object, the principles of precision, interlocking geometry, and seismic resilience converge, which leads to the deeper ambiguity. Is the 12-angled stone merely an extraordinary example of craftsmanship, an impressive but practical solution to structural demands? Or does its deliberate complexity suggest encoded knowledge, an intentional expression of principles understood at a sophisticated level and embedded into stone as both function and message? The answer remains embedded within the wall itself: 12 angles, 12 contacts, one integrated system. And the question lingers in the geometry. Was this simply the outcome of skilled labor, or a deliberate articulation of knowledge shaped into enduring form? To understand these walls fully, one must step back from the stone and look instead at the land itself. Because the architecture of Machu Picchu does not appear imposed upon its environment, It appears drawn from it. The terraces follow the contours of the mountain. The buildings align with ridgelines. Pathways curve naturally with the slope. Even the orientation of structures reflects a dialogue with the surrounding peaks and valleys. This is not a city laid across terrain in disregard of topography. It is a settlement integrated into it. The site sits between dramatic elevations, where steep gradients would normally make construction unstable. Yet instability becomes opportunity. The Inca transformed incline into infrastructure. Instead of flattening the mountain entirely, they sculpted it. Terraces step downward in layered sequences, each retaining soil, each reinforcing the next. These platforms are not decorative gardens, they are structural devices. Terracing performs several functions simultaneously. First, it stabilizes slopes. By cutting the mountain into horizontal steps, the Inca reduced the risk of landslides. Each terrace acts as a retaining wall, distributing pressure laterally rather than allowing it to accumulate downward. Second, it improves agricultural productivity. The terraces create microclimates, differences in sun exposure, drainage, and soil composition. This allows diverse crops to be cultivated at varying elevations within a compact space. Third, and perhaps most importantly from an engineering perspective, terracing modifies how water moves across the landscape. In mountainous regions, rainfall can rapidly erode unprotected soil. Water accelerates downhill, carving channels and destabilizing slopes. At Machu Picchu, water management appears to have been carefully integrated into the design. Spring-fed systems channel water through stone-lined aqueducts. Natural springs were identified and incorporated into the city's layout. Rather than resisting water's presence, the builders controlled its path. Channels direct flow along predetermined routes, reducing erosion while ensuring supply. Fountains distribute water sequentially, suggesting a planned sequence of usage. The relationship between architecture and hydrology is not incidental. It reflects systemic planning. Structures are positioned to accommodate drainage. Roofs likely directed rainfall into collection systems. Subsurface layers beneath terraces include gravel and drainage materials that allow water to pass through without accumulating pressure behind retaining walls. This prevents hydrostatic buildup, which can compromise stability in slope-based construction. In modern geotechnical engineering, drainage is a foundational principle. Water is often the primary cause of structural failure in hillside developments. By controlling its movement, engineers preserve stability. The Inca appear to have applied similar logic, embedding drainage pathways directly into the built environment. This integration extends beyond water. The city's layout responds to the mountain's geometry, rather than reshaping the terrain to match. Architectural ideals, the builders adapted their design to existing features. Natural rock outcrops were incorporated into walls. Ideals, the builders adapted their design to existing features. Natural rock outcrops were incorporated into walls. Large stones were used as anchors. Some structures appear to emerge from bedrock itself. This approach suggests a philosophy of collaboration with terrain. As one modern observer summarized, they didn't try to dominate the landscape, they collaborated with it. The statement captures an essential difference in approach. Many civilizations historically sought to impose symmetry or grid systems onto uneven land. The Inca, by contrast, seem to have treated the environment as a partner in construction. This partnership is evident in orientation as well. Certain structures align with prominent mountain peaks. Others appear positioned to frame solar events. The alignment of buildings with natural features suggests that geography influenced spatial organization. From an engineering standpoint, this makes practical sense. Mountain ridges can serve as windbreaks, slopes can facilitate drainage, elevated positions can reduce flood risk. By placing structures in harmony with these features, builders reduce environmental stress on the architecture. But harmony also has structural consequences. If terrain dictates placement, then load distribution must adapt accordingly. Foundations must conform to uneven substrates. Walls must respond to varying ground stability. In such conditions, flexibility becomes essential. Rigid, uniform designs would struggle to accommodate the irregularities of mountain geology. The result is architecture that integrates with geological structure. The mountain is not merely a backdrop, it is part of the foundation. This relationship may also influence seismic performance. Buildings anchored into bedrock rather than loose soil often experience improved stability during earthquakes. Bedrock transmits motion differently, and secure anchoring reduces differential movement between structure and ground. At Machu Picchu, many walls are constructed directly upon or adjacent to exposed rock formations. This reduces reliance on artificial foundations and leverages the mountain's inherent stability. The engineering implications are significant. When water flow, slope stability, structural support, and seismic considerations are addressed simultaneously, the architecture becomes an environmental system rather than a collection of isolated buildings. Everything is connected. Terraces reinforce slopes, drainage protects foundations, stone geometry resists seismic stress, orientation aligns with natural features. Together, these elements create a resilient network embedded in the landscape. This systemic integration distinguishes the site from many other forms of ancient construction. It is not simply about building durable walls. It is about shaping the environment so that the environment supports the structure. The land becomes infrastructure. This raises a deeper consideration. If the terrain shaped the architecture so thoroughly, then the engineering itself may have been constrained and guided by environmental realities. Steep slopes demand terracing. Heavy rainfall demands drainage. Seismic activity demands flexibility. High-altitude conditions demand efficient spatial organization. In that sense, the engineering solutions are responses to environmental pressure, but responses, repeated over generations, can become refined strategies. What begins as adaptation can evolve into mastery. At sites such as Cusco, urban planning reflects similar integration. Streets follow terrain contours. Walls incorporate natural rock formations. Water systems are embedded rather than appended. This suggests continuity of principle across regions. Architecture is not separate from geography. It emerges from it. Yet this integration introduces a compelling question. If the land dictated many aspects of design, slope, drainage, orientation, foundation, then how much of the engineering was independent choice and how much was environmental necessity? Did builders invent solutions freely, or were they guided by constraints so strong that only certain forms could survive? The answer may lie in the balance between limitation and creativity. Constraints do not eliminate design, they shape it. The mountain did not provide instructions, but it established conditions. Within those conditions, the Inca developed methods that transformed vulnerability into stability. Terraces became structural reinforcements. Water became a managed resource. Rock became foundation. The result is not domination of nature nor passive submission to it. It is adaptation elevated to system-level design. And as one observes the alignment of structures with peaks, the careful channeling of springs, and the layered reinforcement of slopes, another question emerges. If the architecture was shaped so deeply by terrain, was the engineering simply reacting to the land's demands, or did it reflect an intentional philosophy of working with geological forces, embedding resilience by aligning human design with the rhythms of the mountain itself? To understand the endurance of these walls, we must descend beneath them, because their stability is not only a matter of stone geometry or architectural design, it is also a consequence of the ground they stand upon. The Andes are not an accidental mountain chain. They are the product of immense tectonic forces, specifically the subduction of the Nazca Plate beneath the South American plate. This process forms part of the Pacific Ring of Fire, one of the most geologically active regions on Earth. Earthquakes, volcanic activity, crustal deformation, these are not rare events here. They are structural features of the continent itself. The region surrounding sites such as Machu Picchu and Sacsayhuaman has experienced seismic activity throughout recorded history. The ground does not remain still for centuries at a time. It moves subtly or violently, depending on tectonic stress accumulation and release. Any architecture built here must therefore contend with motion as a permanent environmental condition. But geology offers more than instability. It also offers materials. The Andes contain significant deposits of quartz, a mineral abundant in many igneous and metamorphic rocks in the region. Quartz is not only structurally durable, it possesses a property known as piezoelectricity. When mechanical pressure is applied to quartz crystals, they can generate a small electrical charge. This phenomenon occurs because of the mineral's crystalline structure, which lacks a center of symmetry. Under stress, the internal charge distribution shifts, producing measurable electrical potential. This is not speculation. It is a well-documented physical property used in modern technology. Quartz crystals are employed in oscillators, sensors, and timing devices precisely because of their predictable electrical response to mechanical deformation. In geological contexts, large-scale stress within quartz-bearing rocks can produce localized electrical effects. During tectonic pressure buildup, microfractures and deformation can induce electrical signals. Some researchers study these phenomena as part of earthquake precursor research, exploring whether measurable electrical anomalies may correlate with seismic activity. The field remains complex and not fully resolved, but the underlying physical principle is established. When rocks containing quartz are compressed, electrical charges can emerge. Now consider the broader geological environment beneath the Inca walls. The bedrock of the Cusco region includes various igneous formations. If quartz-bearing stones are present in the foundations or surrounding geology, then tectonic stress could, in theory, generate subtle electrical activity in the subsurface during seismic strain. This does not imply that ancient builders designed structures to exploit piezoelectric effects. There is currently no empirical evidence to support such a claim. However, the geological reality of the region includes both frequent tectonic movement and quartz-rich formations. The intersection of those two factors is scientifically relevant. Some reports over the years have described localized magnetic anomalies in areas around Sacsayhuaman. Magnetic irregularities can arise from many causes: variations in mineral composition, iron content in rocks, subsurface structures, or even measurement conditions. The presence of magnetite or other ferromagnetic minerals can influence local magnetic readings. Geological surveys in complex mountainous terrain often reveal heterogeneous magnetic signatures due to natural variations in rock types. It is important to distinguish between documented geophysical phenomena and interpretation. Magnetic anomalies, when measured, typically require careful, controlled surveys to determine their origin. They do not automatically imply unusual energy effects or unexplained forces. Nevertheless, the idea that the walls exist within a dynamic electromagnetic environment is consistent with modern geophysics. The Earth itself has a magnetic field generated by movement in its molten outer core. This geomagnetic field interacts with solar radiation and influences the planet at large scales. Local variations in magnetic readings can occur due to geological structures, mineral distributions, and tectonic features. The Andes, being tectonically active, also experience crustal stress variations. Stress accumulation and release during seismic cycles involve enormous mechanical forces. In regions containing quartz, these stresses can generate small electrical potentials at microscopic scales. But it is crucial to remain grounded in evidence. There is currently no confirmed scientific data demonstrating that the stone walls at Sacsayhuaman or Machu Picchu are responding to electromagnetic forces in any measurable structural way beyond standard geophysical conditions. The durability of the walls is well explained by mechanical design, material properties, geometric interlocking, drainage engineering, and seismic adaptability. The presence of quartz in the region does not imply intentional electromagnetic engineering. However, it does remind us that these structures exist within a complex geophysical system. The earth beneath them is not static stone. It is a dynamic crust under constant tectonic stress. It transmits seismic waves. It experiences strain accumulation. It contains minerals capable of physical responses under pressure. The environment is mechanically active at multiple scales. The Inca builders constructed their architecture in direct contact with this system. That alone is significant, because building in such a region requires awareness, whether explicit or experiential, of the Earth's behavior. Structures must accommodate ground movement, subsurface variation, and hydrological flow. Foundations must tolerate shifts, walls must absorb vibration, drainage must prevent destabilization. The walls do not float above geology, they are anchored within it. This integration means that any response they exhibit during earthquakes is fundamentally a mechanical interaction between structure and crust. The seismic waves originate in tectonic processes. The buildings react according to their geometry and material properties. The surrounding geology influences how those waves travel. In regions rich in quartz, piezoelectric effects may occur at microscopic levels during stress events. But these effects are typically subtle and not known to generate large-scale structural behavior. Still, the presence of such properties adds another layer to the geological complexity of the site. The Earth here is not inert. It is active, mineral-rich, and tectonically stressed, and the architecture is embedded within that environment. This leads to a deeper reflection. When we observe these walls surviving repeated earthquakes, we attribute their resilience primarily to engineering, polygonal geometry, inward-leaning walls, composite cores, precise stone fitting, and drainage systems. These features are sufficient to explain their performance under seismic stress. But the fact that the structures exist within a geologically dynamic region invites curiosity about how deeply builders understood their environment. They could not control tectonic plates. They could not alter crustal movement, but they could design structures that respond intelligently to it, which raises a careful question. Are these walls responding only to earthquakes in the mechanical sense, absorbing vibration, redistributing stress, and returning to equilibrium? Or are they part of a broader interaction with the Earth's physical processes, shaped by geological forces that include not only motion, but mineral composition, stress fields, and magnetic properties? The evidence strongly supports the first explanation, mechanical resilience through design. The second remains a subject of scientific exploration in geophysics, not architectural theory. And yet, standing amid these stones, surrounded by mountains shaped by tectonic collision, one cannot ignore the deeper reality. The walls are not isolated objects. They are part of a living crust, built upon moving plates, in a landscape where the Earth itself is in motion. Which leaves us with a question that remains grounded in science, yet expansive in scope. Are these structures merely enduring earthquakes through engineering alone, or are they expressions of a civilization that learned to build within the Earth's dynamic system, aligning architecture with the physical realities of a planet that never truly stands still? When examining monumental sites such as Machu Picchu and Sacsayhuamán, some observers move beyond structural analysis and enter a more speculative domain. Over the past century, certain theories have proposed that ancient monuments were intentionally placed within networks of terrestrial energy. One of the most well-known of these ideas originates with the early 20th century researcher Alfred Watkins. Watkins introduced the concept of ley lines, suggesting that ancient sites in Britain appeared aligned along straight geographic pathways. He interpreted these alignments as evidence of deliberate landscape planning. Over time, the idea expanded beyond its original archaeological framing and evolved. into broader claims about Earth energy grids. In more modern interpretations, some writers describe networks of Earth energies or vortex sites, proposing that certain locations concentrate subtle forces. According to these views, monuments were constructed at points where energy is said to intersect or intensify. In popular culture, such sites are sometimes described as producing heightened experiences for visitors, sensations of warmth, tingling, emotional elevation, or even euphoria. At locations like Machu Picchu, visitors frequently report strong subjective impressions. The dramatic landscape, altitude, and visual scale can produce physiological responses. High elevation alone can influence breathing patterns, heart rate, and perception. Environmental factors such as temperature shifts, wind patterns, and atmospheric conditions can also affect sensory experience. Some proponents of energy grid theories point to anecdotal accounts of dowsing rods reacting near ancient stone structures. Dowsing, a practice involving handheld rods or pendulums, has historically been used in attempts to locate water or minerals. When rods move, practitioners interpret this as interaction with subterranean energy. However, controlled scientific studies have not demonstrated consistent evidence that dowsing detects unknown physical forces. Movements are widely attributed to the ideomotor effect, a psychological phenomenon in which subtle, unconscious muscle activity produces motion without deliberate intent. Balanced analysis requires acknowledging alternative explanations. Environmental factors can produce measurable physical phenomena that might be interpreted subjectively. Infrasound, sound waves below the threshold of human hearing, can arise from wind interacting with terrain, water flow, or structural vibrations. Infrasound has been studied for its potential to influence mood and perception. Certain frequencies can produce feelings of unease or physiological discomfort. Mountainous landscapes with wind channels and flowing water systems can generate complex acoustic environments. Similarly, electromagnetic fields exist naturally across the Earth. The planet's magnetic field interacts with solar activity and geological structures. Local variations can occur due to mineral composition in bedrock, including iron-bearing formations. These variations are part of normal geophysical processes. There is no established scientific evidence that ancient monuments are positioned to harness unknown global energy grids, but measurable magnetic fluctuations can occur in any mineral-rich region. It is also important to consider cognitive factors. Human perception is highly sensitive to context. When individuals visit historically significant sites, expectations, narratives, and environmental cues can shape experience. The combination of scale, history, altitude, and landscape can produce emotional responses that feel profound. Such responses do not require external energy explanations. They can emerge from psychological and physiological integration. This does not diminish the impact of the sites. It simply situates that impact within known mechanisms. However, the speculative hypothesis remains culturally influential. The idea of Earth energy grids suggests that ancient builders possessed knowledge of invisible forces and deliberately constructed monuments to align with them. In this view, architectural placement becomes not only structural or astronomical, but energetic. From a scientific standpoint, claims of global energy networks lack empirical verification. Geological surveys, satellite measurements, and geophysical studies have not identified a coherent planet-wide grid system influencing monument placement. Alignments that appear significant may arise statistically from the large number of ancient structures and natural topography. Yet the persistence of such theories raises a philosophical question rather than a strictly physical one. What does it mean that people across cultures report sensations of intensity at certain locations? Is it purely suggestion, environmental influence, or does human perception respond to subtle combinations of factors that we do not fully integrate consciously? At high-altitude sites like Machu Picchu, physiological effects of reduced oxygen can alter perception. Mild hypoxia can influence mood, cognition, and sensory processing. Combined with dramatic visual stimuli, sheer cliffs, cloud movement, expansive views, the result can feel transcendent. None of these effects require unknown energy sources. They require environment. Still, the experience of visitors remains real, even if the interpretation varies. The tension lies not in dismissing subjective reports, but in distinguishing between experience and mechanism. Science operates through measurement, repeatability, and falsifiable hypotheses. Energy grid claims in their strongest forms have not met those criteria in controlled investigations. However, the broader idea that ancient builders were sensitive to environmental cues beyond simple geometry remains plausible. Builders in mountainous regions must understand wind, water flow, sunlight patterns, soil stability, and seismic risk. Over generations, such sensitivity can become refined into architectural tradition. This does not imply mystical perception. It implies environmental literacy. It is conceivable that certain sites were chosen because they felt significant, perhaps due to visibility, water access, defensive advantage, or agricultural suitability. Over time, cultural meaning may accumulate around those locations, reinforcing their importance. The result can appear intentional at a symbolic level, even if the underlying factors are practical. When evaluating energy hypotheses, caution is essential. Extraordinary claims require strong evidence. At present, there is no validated data demonstrating that Inca monuments were engineered to interact with unknown Earth energy grids. The structural resilience of the walls can be explained through well-established principles of geometry, material science, seismic engineering, and hydrological management. Nevertheless, the question persists in cultural discourse. What we feel is not always directly aligned with what we can measure. Human perception integrates multiple sensory inputs, environmental conditions, and cognitive expectations. Experiences of awe, elevation, or intensity can arise from known mechanisms without invoking unverified forces. This distinction is crucial. Science does not deny subjective experience. It seeks to understand its causes. In regions shaped by tectonic movement, mineral diversity, altitude, and dramatic landscapes, it is unsurprising that visitors report strong impressions. The combination of geological instability and architectural precision can amplify the sense of encounter with something profound. Whether that profound feeling originates in psychology, environment, or a blend of both remains open to investigation. But the evidence does not currently support the existence of measurable Earth energy grids influencing monument placement, which brings us to the deeper reflection underlying the speculation. Did ancient builders sense something we no longer perceive? It is possible that they were more attuned to environmental cues simply because their survival depended upon it. Without modern infrastructure, understanding terrain, water flow, and seasonal cycles was essential. Sensory awareness, refined through necessity, could have guided construction decisions that later generations interpret as energetically aligned. This interpretation requires no unknown forces, only attentive observation. The mystery, then, may lie not in hidden energies beneath the stones, but in the depth of human perception itself, and in how closely early builders listened to the land around them. To understand the walls of the Inca world, we must resist the temptation to treat them as an isolated miracle. Civilizations do not appear fully formed. They evolve within long arcs of cultural exchange, experimentation, adaptation, and loss. When we examine the precision of Inca masonry at sites such as Machu Picchu and Sacsayhuaman, we are observing the endpoint of a much longer architectural tradition. One explanation is emergent genius through gradual trial and error. In this model, communities refine techniques over generations. Early structures may have been simpler, rubble cores, mud mortars, less precise stone dressing. Through repeated seismic experience, builders learn which forms endure. Over centuries, unstable designs fail, while more resilient geometries survive. Knowledge accumulates not through sudden discovery, but through selection. The environment becomes a teacher. Earthquakes eliminate weak constructions. What remains is what works. This evolutionary model of engineering is consistent with how many technologies develop. Agriculture, metallurgy, navigation, and mathematics all show incremental improvement over time. There is no requirement for sudden leaps. Instead, practical constraints shape innovation. In a seismically active region, structural flexibility would not be optional. It would be essential. Over time, builders would increasingly prioritize interlocking geometry, inward wall angles, and tight stone fitting. A second possibility involves inherited knowledge from earlier cultures. The Inca Empire did not arise in a vacuum. It expanded across regions that had long-established civilizations. Among these were the Tiwanaku culture near Lake Titicaca and earlier Andean societies. Architectural traditions often persist across political transitions. When empires rise, they frequently adopt and adapt the techniques of those who preceded them. Sites such as Tiwanaku demonstrate advanced stonework predating the Inca expansion. Massive blocks, carefully shaped surfaces, and sophisticated urban layouts suggest that high-level masonry skills existed in the Andes long before the Inca state consolidated power. Cultural continuity in the region may have allowed construction knowledge to flow across generations and political boundaries. This raises an important historical principle. Technological capability often outlives specific empires. When a civilization collapses or transforms, knowledge does not necessarily disappear completely. It can persist in craft traditions, oral transmission, or regional expertise. The Inca may have inherited techniques refined by earlier cultures, integrating them into their own administrative and architectural systems. A third explanation acknowledges the possibility of lost techniques, not mysterious in origin but simply undocumented. The Inca did not develop a fully standardized written language system comparable to alphabetic scripts. Their record-keeping relied heavily on quipu, knotted cord systems used for accounting and administration. While quipu were highly sophisticated, they did not preserve architectural blueprints in the modern sense. Construction knowledge may have been transmitted through apprenticeship rather than formal diagrams. In such systems, expertise is embodied in skilled labor rather than archived in manuals. When master builders train apprentices directly, precision can be maintained without written plans. However, if social disruption occurs, specialized knowledge can decline or fragment. The absence of preserved technical documentation does not imply the absence of technical understanding. Another perspective considers misinterpretation of what is actually achievable with available tools. Modern observers sometimes assume that precision below a millimeter requires steel machinery, yet experimentation has shown that stone, copper tools, abrasive sands, and patient polishing can achieve remarkable tolerances. When combined with iterative fitting, placing a stone, marking contact points, removing it, refining surfaces, the result can approach exceptional precision. The key factor is time. High precision does not require advanced metallurgy if sufficient labor, organization, and patience are available. In a state-level society with coordinated workforce systems, large construction projects can mobilize thousands of workers. The engineering challenge becomes organizational rather than technological. Infrastructure, logistics, and administrative control can enable outcomes that appear extraordinary from a modern individual perspective. The comparison to earlier Andean sites complicates the narrative further. At Pumapunku, stone blocks display complex shaping and precise joints. Some stones are carved with angular recesses and interlocking features. These structures are often cited in discussions about advanced pre-Columbian engineering. While interpretations vary, the existence of sophisticated masonry across multiple sites suggests a regional tradition rather than an isolated anomaly. When we place Tiwanaku, Pumapunku, Cusco, and Machu Picchu within a broader timeline, a continuum of knowledge becomes plausible. Rather than viewing the Inca as sudden innovators, we can consider them as inheritors of a long-standing architectural culture. Techniques could have evolved gradually, diffused across communities, and been refined through regional adaptation to seismic conditions. This continuum model does not require lost advanced technology. It requires sustained craftsmanship. Stone dressing, geometric understanding, and structural adaptation can develop over centuries without interruption. Each generation builds upon the practical experience of the previous one. The result may appear sudden in the archaeological record if earlier phases used less durable materials that did not survive. There is also the possibility that modern assumptions underestimate pre-industrial capabilities. Contemporary engineering relies on mechanized equipment, but precision is not exclusively a product of machines. Human hands, guided by skilled observation and iterative correction, can achieve high levels of accuracy. The difference lies in scale and efficiency, not in fundamental possibility. Scientific studies of seismic performance in Inca walls support mechanical explanations. The interlocking polygonal geometry, absence of continuous vertical joints, and slight inward wall inclinations distribute stress during ground motion. These features reduce the likelihood of catastrophic collapse. The engineering principles are consistent with known structural dynamics. They do not require unknown technologies. Thus, the central debate narrows. Were the Incas architectural pioneers who independently developed sophisticated seismic design through experience and adaptation? Or were they beneficiaries of accumulated knowledge transmitted across earlier Andean civilizations, refined and institutionalized under imperial organization? Both explanations are compatible with the physical evidence. Neither requires extraordinary assumptions. The masonry itself does not demand lost civilizations or external intervention. It demonstrates advanced craftsmanship within the constraints of available materials and environmental demands. The deeper synthesis may be this: innovation rarely belongs to a single moment. It is typically distributed across time. Cultural memory, apprenticeship systems, environmental pressure, and political stability all contribute to technical continuity. The Inca Empire, at its height, may have consolidated and standardized techniques that had already matured regionally. When we observe the precision of their stonework, we are not necessarily witnessing the beginning of a tradition. We may instead be seeing its culmination. Which leads to a historical question grounded in evidence rather than speculation. Are the Incas the originators of this masonry tradition? Or are they the inheritors of centuries, perhaps millennia, of accumulated Andean engineering knowledge, refined through continuous adaptation to one of the most geologically demanding landscapes on Earth? In the modern era, with laser scanners, CNC milling, diamond-tipped cutting tools, and computer-aided design, one might assume that replicating Inca masonry would be straightforward. Yet attempts to reproduce the same level of irregular multi-angled precision, particularly in large-scale polygonal assemblies, have repeatedly revealed unexpected difficulty. The challenge is not merely shaping a stone block to a desired dimension. Modern machinery excels at producing standardized geometry: straight edges, flat planes, right angles, predictable tolerances. Industrial systems are optimized for repeatability. When a design is defined in digital coordinates, a machine can reproduce it with extraordinary consistency. That is the strength of contemporary engineering. But the Inca approach did not rely on standardization. Each stone in many polygonal walls appears individually tailored to its neighbors. The faces are not uniform modules. They are unique forms, shaped to interlock with adjacent blocks in complex non-linear arrangements. There are no continuous horizontal seams running unbroken across long distances. Instead, joints shift, angles vary, and surfaces adapt. Modern construction philosophy often prioritizes speed, scalability, and interchangeability. Blocks are cut to consistent dimensions so that assembly becomes efficient. Mortar compensates for minor irregularities. Structural systems are designed around load calculations that assume uniformity. The goal is predictability. In contrast, the Inca method appears to have embraced iteration. Stone placement likely involved repeated adjustment. A block would be set in position. Contact points would be identified. Material would be removed gradually. The stone would be repositioned. The process would continue until the surfaces aligned with minimal gaps. This requires time-intensive craftsmanship. It demands patience at every stage. Modern reconstruction efforts sometimes attempt to replicate these walls using advanced equipment. Even with heavy machinery, achieving comparable irregular fits between large, multi-angled stones can prove challenging. Machines are highly effective at producing flat surfaces and geometric regularity. They are less optimized for creating complex organic interlocking forms that require continuous adjustment against neighboring blocks. This difference reflects two distinct engineering philosophies. Contemporary systems emphasize efficiency through uniformity. Inca construction appears to have emphasized structural performance through adaptation. Instead of forcing stones into standardized shapes, builders may have allowed each block to respond to the specific geometry of its surrounding environment. The result is a wall that behaves as a continuous, integrated structure rather than a collection of identical units. The resilience of these walls under seismic stress is linked to that integration. Slight irregularities can distribute force across multiple contact points. When earthquake waves travel through rigid, uniform joints, stress can concentrate along predictable lines. In a highly standardized system, failure often follows those lines. In a multi-directional interlocking system, stress paths become more diffuse. Modern engineering does incorporate concepts of flexibility and damping, especially in earthquake-resistant design. Base isolation systems, energy-dissipating joints, and composite materials are widely used in seismic regions. These solutions often involve complex calculations and advanced materials, yet the underlying principle, allowing controlled movement to prevent catastrophic failure, echoes features visible in Inca masonry. Despite this conceptual similarity, replicating the precise aesthetic and structural integration of these walls remains difficult. Part of the challenge lies in the relationship between design and execution. Today, design is often separated from construction. Architects create models, engineers calculate loads, machines fabricate components, contractors assemble them. The workflow is fragmented and highly specialized. In the Inca context, evidence suggests a more integrated system. Craft expertise, structural knowledge, and on-site adjustment may have been unified within coordinated teams. Knowledge was likely transmitted through apprenticeship and direct supervision. This system depends on human continuity rather than digital documentation. The real machine was not a tool, it was a system of people and knowledge. That statement captures a critical distinction. Modern society frequently equates technological advancement with mechanical power, but complex outcomes do not always require complex machines. They require organized intelligence applied consistently over time. Heavy equipment today can move massive stones. It can shape granite with precision. It can replicate geometric patterns with exact measurements. Yet when tasked with producing large-scale, irregular polygonal assemblies that interlock uniquely without standardized repetition, the process becomes less about raw capability and more about workflow design. Efficiency in modern construction is measured by time, cost, and scalability. In contrast, Inca construction may have prioritized durability and environmental integration over rapid completion. A wall that takes longer to build but withstands centuries of seismic activity represents a different optimization strategy. This leads to a broader reflection on industrialization itself. Standardization has transformed architecture, infrastructure, and global development. It enables mass housing, rapid urban growth, and predictable supply chains. Without it, modern cities would not function at their current scale. Predictability reduces uncertainty. Interchangeable parts simplify repair and expansion. However, standardization also imposes constraints on form. When components are designed for interchangeability, uniqueness decreases. Irregular geometry becomes costly. Energy must be redirected, absorbed, or dispersed. Structures that integrate with their environment tend to endure longer under dynamic conditions. The ancient builders may not have expressed this in mathematical terms, but through observation, iteration, and experience, they arrived at solutions that function in harmony with the Earth's behavior. This does not require lost technologies or extraordinary explanations. It requires sustained attention to environmental feedback over generations. Structures that failed would have revealed weaknesses. Those that survived would have informed future design. Over time, knowledge accumulates through consequence. The walls are therefore not simply stone assemblies. They represent institutional memory encoded in architecture. Each interlocking block is part of a larger system shaped by climate, geology, and human labor. The stones are heavy, yes, but weight alone does not explain endurance. Their geometry matters. Their placement matters. Their relationship to terrain matters. Flexibility over rigidity, adaptation over domination. These principles are visible throughout the construction. Consider how the stones distribute force across multiple contact points. When seismic waves pass through, energy is not confined to a single joint. Instead, it flows across surfaces, shifting direction as it encounters irregular angles. The absence of uniform seams prevents stress from aligning along a single failure path. This distributed interaction resembles modern concepts in structural engineering, yet it was achieved with tools and systems far removed from contemporary machinery. The achievement, then, is not technological spectacle, it is environmental intelligence. The builders understood the Earth's behavior through lived experience. They constructed in a region defined by tectonic motion, seasonal variation, and mountainous terrain. Their architecture reflects adaptation to those realities. Perhaps the most profound lesson is this: durability arises not from resisting nature, but from participating in it. Rigid systems attempt to impose stability externally. Adaptive systems derive stability internally through interaction. The walls stand because they move slightly. They endure because they can respond. They survive because they are not isolated from the forces around them. When we examine them through this lens, the mystery shifts. The focus moves away from speculation about hidden energies or lost super technologies. Instead, it centers on human capacity, observation, patience, coordination, and accumulated knowledge applied consistently over time. The stones are silent witnesses to that process. Each block represents labor. Each joint represents adjustment. Each alignment represents decision-making under environmental constraints. The walls embody a relationship between human intent and planetary dynamics. That relationship is the true architecture. Perhaps the most important realization is that moving stone was never the ultimate achievement. Stone can be lifted by many methods. What distinguishes these structures is not their mass, but their integration. Understanding the Earth, its seismic rhythms, its terrain, its water flow, its material properties, was the foundation of their success. The builders aligned their work with those realities rather than attempting to override them. In doing so, they produced structures that remain functional centuries later, not because they defied earthquakes, but because they were designed to live with them. The walls are therefore not monuments to conquest over nature. They are monuments to dialogue with it. They demonstrate that resilience can emerge from flexibility, that strength can reside in controlled movement, and that intelligence in architecture is measured not by rigidity but by responsiveness. When seismic waves pass through these structures, they do not encounter resistance in the conventional sense. They encounter geometry prepared to accommodate them. This is the quiet genius embedded in the stone. No slogans, no spectacle, only alignment between human craft and geological reality. As we step back from the walls, the broader implication becomes clear. Innovation does not always mean adding complexity. Sometimes it means refining relationship. Sometimes it means listening more closely to the environment and designing accordingly. The Inca builders achieved something enduring not by overpowering their landscape but by integrating with it. Their walls remain because they were conceived within the constraints and opportunities of a dynamic earth. Which brings us to the final reflection. These walls do not just stand, they listen. Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.